and welcome to CO 738 Probabilistic Methods. Today we'll be discussing the second moment method. What is a second moment? Well, more generally, the kth moment of a random variable x is e of x to the k, the average mean expectation equivalently of this kth power of x. So thus the second moment is the expectation of x squared. Now that's related to another well-known probability term known as the variance. The variance of a random variable x is denoted var of x, is the expectation of x minus e of x squared. So what is that? That's the average of the squared distance from the mean. Now, when we take the square root, the positive square root of the variance, that's called the standard deviation, another well-known term from probability. And for our purposes today, and perhaps going forward, when the random variable is clear, we're going to typically let mu denote the expectation and sigma the standard deviation. So the second moment method involves studying the variance. Now, what is that? How are we going to use it? It's related to a certain inequality. In particular, we first need to tell you about Markovs inequality. The most basic inequality in probabilistic methods is Markovs inequality, which is used the first moment. So not about the second moment, but the first moment. It says that if x is at least 0, is a random variable, so that means it's a non-negative random variable, then for every a greater than 0, the probability that x is at least a is at most the expectation of x divided by a. So you can't be too many times the expectation if you're a non-negative random variable. What's the proof of this? Well, if you haven't seen it before, you might want to pause for a moment and go ahead and try to prove this fact. All right, I'll go on ahead with the proof. Well, this just follows really from the definition of expectation. The expectation of x, you might recall, is the sum of I times the probability that x equals I, which, since we're non-negative, we can remove the lower terms, since they're only positive, and find that we're greater than equal to the sum when I is at least a of I times the probability of x equal I. And then since I is at least a for all those terms, we know this is at least a times the sum of those terms, which is the probability that x is at least a. And so then we just rearrange to get Markovs inequality. So it's a simple manipulation of the expectation. So this is core to the so-called first moment method, where one studies the expectation and uses it to derive something about probabilities. Instead, we'll be looking at the second moment, something called Chebyshevs Inequality, which involves the second moment. What does it say? It says that for all lambda greater than 0, the probability that x minus mu is at least lambda sigma is at most 1 over lambda squared. So that the distance from the mean mu, if it's at least lambda standard deviations, it's at most 1 over lambda squared. What's the proof of this? Well, we look at the variable x minus mu squared, which is non-negative as it's a square. So we can apply Markovs to it, and hence we find that the probability x minus mu is absolute value is at least lambda sigma. Well, you just square that, so you get the probability x minus mu squared is at least lambda squared sigma squared, which by Markovs is the expectation of x minus mu squared over lambda squared sigma squared. So here we're taking a to be lambda squared sigma squared. And then you realize the numerator is sigma squared, it cancels, you get 1 over lambda squared as desired. So that's the proof of Chebyshevs inequality. We're going to continue on now with some notes about Chebyshevs. So what does it say? It says that Chebyshevs says the probability decreases at least quadratically in the number of standard deviations. So that's nice. Is that tight? The answer is yes. For example, the random variable x, which is mu plus lambda with probability 1 over 2 lambda squared, mu minus lambda with probability 1 over 2 lambda squared, and mu otherwise. If you calculate the variance and therefore standard deviation, you'll find indeed that this will show that Chebyshevs is tight. However, generally, sometimes we can do better. So for example, when you're the normal distribution, this probability is actually 2 the integral from lambda to infinity of the normal distribution, 1 over root 2 pi e minus t squared over 2 dt, which you can work out to be approximately root 2 over pi e to the minus lambda squared over 2 divided by lambda. That is, it's exponentially decreasing in lambda. And more generally, we'll see later in this course that when x is the sum of nearly independent random variables, such exponentially decreasing bounds can be obtained. So often we can do better than Chebyshevs, but without any restrictions, Chebyshevs is essentially the best one we can do for probability distributions. All right, so now let's go ahead and talk about how do you calculate the variance. So formulas for variance and covariance. So an important concept that we're going to need is that of covariance. So the covariance of two random variables y and z, which we'll denote as cov of yz, is the expectation of y times z, that's the product there, minus the product of their expectations. So what is this tracking? It tells you, in some sense, how dependent they are on each other. In particular, if y and z are independent, then the covariance of yz is equal to 0. So what good is that? Well, for example, we have this nice proposition that if x is the sum of random variables, x1 up to xn, then you can calculate the variance of x. It's simply equal to the sum of the variances of the xi plus the sum of the covariances, where of I not equal to j of covariance of xi xj, and those are going to be ordered pairs. So each pair will show up twice. And you can easily just derive this from the various definitions of variance and covariance, so I won't do that. Instead, I will note, though, what is variance typically. So if xi, for example, is an indicator random variable with probability pi, you can check that the variance of xi is pi times 1 minus pi by just calculating out the various squares there. And that's, of course, at most pi, which is the expectation of an indicator random variable there. And so generally, if these xi are indicator random variables, then the variance of x is at most, the first term in the sum just sums up to the expectation of x, and thus we have your most the expectation of x plus the sum of these covariances. So generally, for these indicator random variables, we get these nice formulas. So now that we've seen that, I wanted to move on to our big example for today, which is an example from number theory about prime divisors. So we're going to let nu of n denote the number of primes dividing n, and here we'll do that without multiplicity. It won't make too much difference to the theorem we are going to prove, but let's just do that for simplicity. All right, so then what is our theorem we're going to be proving is a theorem by Hardy and Ramanujan from 1920. Let omega n be an arbitrarily slowly growing function to infinity, then the number of x in from 1 to n such that nu of x minus log n is greater than omega n square root log n is little o of n. So what's another way to say that? It's to say that almost all numbers n have very close to log n prime factors. Right? So if how many are far away here, far only means square root log n, away from log n is little o of n. So almost all of them have very close to log n prime factors. So that's a nice theorem from number theory. We're going to be following a probabilistic proof given by Tehran in 1934. So the original argument was a bit complicated. Here we're going to use probability to give a simple second moment method type proof. What is the proof idea? Well, it's a straightforward application. Namely, we're going to show that the expectation of this nu of x, if you view x as random inside 1 to n, is basically log n plus or minus somewhat kind of little o of 1, or rather big O of 1, but some constant, really. And we're going to use Chebyshevs and the covariance to show that this is indeed concentrated. To show, we're going to apply Chebyshevs Inequality to show that indeed the probability that you're that far away, omega n square root log n, is actually quite small. All right, so that is the plan. Let's proceed with the plan. So we're going to let x be chosen randomly from 1 to n. For p prime, we'll set x of p to be 1 if p divides x and 0 otherwise. So this is an indicator random variable of whether p divides x. And we're going to let m be n to the 1/10, so the 10th root of n. We're going to let x be the sum of these indicator random variables when p is at most m. So what's the point there? We do want to be careful about primes that are too large, as they're going to might be a little hard to handle the covariances of, but as you'll see in a bit, but so we just ignore those. So x is essentially an approximation for nu of x. What you can tell is that x has at most 10 prime factors greater than m, right? You can have at most 10 that are at least n to the 1/10, because then you product those, you'd be bigger than n then. So we know that nu of x minus 10 is at most x of x is at most nu of x. So this x, the sum we're doing, which you can view as a random variable of little x, is is upper bounded by the number of prime factors and lower bounded by the number minus 10. So we'll focus on this x. So what is the expectation of x? Well, we can first look to the expectation of xp. That is, of course, n of p floor divided by n, because that's the number, therefore, of n's that are numbers from 1 to n that have p as a divisor. And that number, of course, is 1 over p, but it might be a little off because of the floor, so it'll be plus, we'll say, 1 over n. And now, what good is that? Well, by linearity of expectation, since these are indicator random variables, we know the expectation of x is simply the sum of these expectation of the xp's, which is the sum 1 over p plus O of 1 over n. The O1 over n term, again, there's at most, m of those terms, so it's, say, at most O of 1. And what about the sum of the 1 over p? You may not know that, but you can derive a number theory that if you sum up the prime, the reciprocals of the prime, so if you sum up 1 over p up to a number n, it's going to be log n, which if you sum them up to m would also be about the same there. All right, so we know the expectation of x is actually log n plus O of 1. Now we'll turn to calculating its variance. So as for the variance of x, we know from our formula, since it's the sum of indicator random variables, is the sum of the individual variances, x of p, and the sum of the covariances, xp, xq. So what are these individual variances? Well, note that the variance of xp is essentially 1 over p times 1 minus 1 over p plus O 1 over n. Why? Because you can think that xp has essentially probability 1 over p, and so as we showed before with indicator random variables, then you get this formula 1 over p, 1 minus 1 over p. So pi is this 1 over p, essentially. All right, so that means that the sum of those individual variances is essentially the sum of the 1 over p's, which is, again, log n, using that theorem from number theory. Okay, so we have this terms for the variance. The sum of the individual variances is roughly also the expectation there. It's this log n. What about the covariances? How do we calculate them? Well, we need to look then when p is not equal to q. What does that mean? Well, xp, xq, this product is what we're interested in. And remember, those are 0, 1 random variables, so we're interested when that product is 1. And it's 1 if and only if both of them are individually 1, which only happens when p divides x and q divides x, and that's equivalent to when pq divides x, just from basic number theory. All right, so that's what we have to work with. Now we can actually basically calculate the covariance. Namely, if you remember the definition of covariance, it's the expectation of the product minus the product of the expectations. And here, that's going to be n over pq floor divided by n, since that's, again, the number of numbers from 1 to n that have pq as a divisor, minus n over p floor divided by n over q floor divided by n. And I claim that's on the order of 1 over n plus or minus. So you'd have to do it differently for upper bounds and lower bounds, but the idea is that these floors essentially throw things off by a 1 over n factor, and so we're going to be off by at most 1 over n, because generally the 1 over pq and 1 over p times 1 over q will cancel out. The prime terms will cancel out, so we're just going to get this little bit of error from the floors. So what does that mean? Well, so we can now look at this sum of those covariances, these terms, and I can just say, well, there's at most m primes, p and q there, so this will be kind of at most m squared times these little error terms, these 1 over n error terms. And what will that give you? That will tell you that since m is, again, n to the 1/10, that we're going to be off by very little. We're going to be off by plus or minus n to the minus 8/10, which of course is little o of 1 as n goes to infinity. So what does all that say? It tells us that the variance, which is the sum again of the individual variances, which was log n plus O of 1, and the little covariances, which are very small, they're in sum only little o of 1, that the variance of x is log n plus O of 1. And now we're almost done, because by Chebyshevs, we know that then applying Chebyshevs, the probability that x minus the expectation, that's log n, is bigger than lambda times the standard deviation, which here its standard deviation would be square root log n, will be less than 1 over lambda squared plus little o of 1. And so then we're done as if lambda is going infinity, this probability is going towards 0. All right, so that is our nice proof using the second moment method. We were able to establish the expectation, the variances of the individual terms, the covariances to get the overall variance, and apply Chebyshevs to get the desired proof. And I'll just point out that Erdos and Kak in 1940 proved something stronger. They showed, actually using some more probability but the same essential ideas, that this nu of x, actually this number of variables with the prime divisors, behaves like a normal distribution, where the mean is this log n and the standard deviation is square root log n. So you can actually go further looking at all of the various moments and determine that they all line up with the normal distribution, and then using some theorems from probability show that then it's actually like the normal distribution. And so in particular, the number of such elements from 1 to n above a certain threshold acts exactly like those integrals for the normal distribution. So you can get better, instead of here quadratically decreasing, we could actually get exponentially decreasing in lambda. So that's all I wanted to say about number theory and this prime divisor example. So it's our first taste of the second moment method. Just wanted to say a little bit at the end here about comparing the first moment to the second moment. So if x is non-negative, then the probability that x is greater than 0 is at most the expectation of x. And we've been using this before. Basically, if you have a proposition then that if x is non-negative and you know the expectation of x goes to 0, so I think of x as some family of random variables with various n's, then it would tell you that x will be 0 almost always. So then indeed the probabilities get very small that x is greater than 0. Now what can you do if the expectation of your random variable actually goes off to infinity, so grows with that? Then, well, that's more complicated. Actually, then x may not be greater than 0 almost always. You're tempted to say, oh, if the expectation goes off to infinity, then surely I must be non-zero. But if you stop and pause and think for a moment, you'll realize there's a random variable, very simple, that shows this not true. Namely, for example, you could have x be n squared with probability 1 over n and 0 other ways. So there could just be one point, for example, that has all of the mass. So here the expectation, of course, would be n, which is going to infinity, but it's 0 with probability 1 minus 1 over n, so it'll actually be 0 almost always. So that's just an example. And what makes this example pathological, what's the problem with it, is that it has high variance. So most of the weight is on 0, but there's this little bit out by n squared. So if you calculate the variance, it's more on the goes very large. It's more in the order of something like n cubed, which is much bigger than, say, the expectation of x squared. And so what we'll look at for a moment is that if the variance is small enough, we may be able to conclude that x is actually greater than 0 almost always. So this is where Chebyshevs comes in, and this is really what is generally meant by the second moment method. So let me prove a theorem. We claim that the probability that x equals 0 is at most the variance of x over the expectation of x squared. How do we prove this? Well, you just apply Chebyshevs with an appropriate lambda, here being mu over sigma, which, again, mu is the mean, the expectation, and sigma is the standard deviation. Then Chebyshevs tells you that the probability that x equals 0 is, of course, at most the probability that x minus mu is at least lambda sigma, which would be that you're at least a mu expectation distance away from the expectation. And then applying that, that's at most 1 over lambda squared. Plugging in lambda being mu over sigma gives sigma squared over mu squared, which is variance over expectation squared, concluding the proof. So what does this tell us? Well, a different way to think about this, a nice corollary, is that if the variance of x is little o of the expectation of x squared, then this says that that probability x equals 0 is really going towards 0. And so then it tells you that x is greater than 0 almost always. And if you stare at that proof above, you'll actually know a bit more is true. that if the variance of x is little o of expectation of x squared, then really you can conclude that x is approximately e of x almost always. What do I mean by that? Well, if you just wanted a distance of epsilon mu away from the mean, you just get an extra epsilon factor, which will be washed out as it goes to 0. And so what can we therefore conclude? That actually x is always 1 plus or minus epsilon expectation of x, that it's e of x plus or minus little o of e of x. So it's really e of x almost always. So that's really the second moment method, is that we can conclude, we can use Chebyshevs inequality, we can use this calculation of variance and covariances to oftentimes show, for example, in the first corollary there, that x is non-negative almost always. So maybe that's the outcome we want, that there's some desirable variable that's positive. Or we can even conclude perhaps that x is actually close to its expectations, so-called concentration, that we're always very close to what we expect almost always. So that concludes our first taste of the second moment method, where we defined variance, we looked at formulas for it, we saw an example that used it, and summarized what the general method is. Next time we'll look a little bit more about its application to random graphs. So until next time, see you then!